Hi, welcome back to this video tutorial series on kinematics of mechanisms, part A, that is introduction and position analysis. So this is video number 3. We'll be covering kinematic pairs and how to find degree of freedom of pair and also what are the types of pairs. So before this we had looked at introduction of this video tutorial series, what is degree of freedom, and also degree of freedom when it comes to a point as well as rigid body. In video number 2 we looked at GeoGebra software and how do you represent a point in 2D and also rigid body in 2D in GeoGebra. Some animation we were able to see. So it's highly recommended that you watch these two videos before you come back to this video number 3. Okay, so let us get back to the digitizer. So I'm going to come up with this word again, kinematic. Kinematic means motion, study of motion, kinematics. Okay, pair means two. So that means we can understand what is the relative motion between two bodies. That is what is a kinematic pair. Relative motion between two bodies. Okay, so the simplest what you would probably remember is, let's say I have a block resting on a plane like this or on a line. So if you have this block, so obviously you may say that there is only one translation that is possible. This is possible. If we think, can we move this up? Yes, we can move it up, but obviously it will lose contact with the surface, so this motion is not possible. Okay, and similarly when I try to rotate this body, the rigid body like this, it will lose contact with the bottom part, so this rotation is also not possible. So the first pair what we have is known as a sliding or prismatic or translatory pair. So the degree of freedom of this pair is basically relative motion possible. How many types of relative motions, or let's say relative motion, I would rather use the word independent relative motions possible. Okay, so that is the degree of freedom definition we'll be using for a kinematic pair. So in this particular case, degree of freedom will be 1. Okay, now let's look at another common form. Let's say I have a rigid body like this and I assign or I attach a revolute joint. Okay, a revolute joint. So this is a rotational or revolute joint. Okay, now what kind of motion is possible? So you can see that I will not be able to translate this in this manner. If I try to translate, I'll be breaking this joint. So this translation is not possible. Similarly, I can't translate vertically up because it will also break the joint. However, I can only do this rotation. So rotation is possible, right? So degree of freedom of this rotational or revolute joint is 1. Okay, now if you remember, we also had another definition of degree of freedom, that is total number of parameters minus number of constraint equations, or I can also say number of restricted motions. Let me try to put it this way: total number of motions minus number of restrictions. Okay, this is one easier way to find degree of freedom of a pair. So in the first case, what had happened? This case, the prismatic one, degree of freedom is, see, if I don't have any connection, if there is a rigid body, I can have three motion. Okay, so degree of freedom was, total number of motions possible was 3, but if I locate or if I place this restriction or constraint, right, so what happens, I will not be able to move vertically up, I'll not be able to rotate. So that means I'll be having two restricted motion. So degree of freedom is 1. That means 1 is allowed. That is what it is. Okay. Similarly, this guy. So if I don't have a joint, okay, there's a rigid body without any joint, so it had 3 motion possible. However, the moment I introduced a revolute joint like this, so what happened is I can't translate. This translation is also not possible. Only this is possible. So again, degree of freedom as per this definition. Earlier total number of motion was 3, but because of the introduction of that joint, I have lost 2 degrees of freedom. So that means degree of freedom is 1. Okay. Now let's look at the same form. This is a slider. I can also draw, sorry, in this manner. Let's say I have a cuboid and there's a hole, again kind of a rectangular hole that is there, and I insert one more part which looks like this. Okay, so this guy, though the diagram looks 3D, but this is considered as a 2D system also. So only motion possible is I can only translate in and out. So translation is possible. Okay, now let us look at a few more kinematics pair so that our clarity is better. Okay, let me try cylinder. So there is a cylinder and there is another cylinder inside this. It goes in this manner. So what happens right now is there's a circular hole here. So one cylinder inside another cylinder. So what happens is I can translate, I can also rotate, right? So these two motions are independent. That means there is a translation and there is also a rotation. Okay, so this is known as a cylindrical pair. And degree of freedom of this is 2. Okay, now let's quickly do the other pairs because now I think you've got an idea what we are dealing with. Let us assume that there is a spherical cavity and within that I have put another hemispherical thing like this. Okay, this is a spherical cavity and there is a spherical body. So it's like this. I have a spherical body and inside a spherical cavity. So if you observe, this is a 3D case. Okay, now in case of 3D, the spherical cavity will have, sorry, the object will have 6 degrees of freedom. I can translate, and I can also have uh, 3 rotations. Okay, so degree of freedom was 6 because it is a 3-dimensional case. However, because of this spherical thing, I can't translate, I can't move it in all the 3 direction. Okay, because I'll be breaking the joint. So these 3 translations are not allowed. Okay, so that means 3 restrictions are there. So the allowed degrees of freedom are 3. What are they? So I can rotate like this, I can rotate like this, and I can also rotate in this manner about this x-axis, y-axis, and z-axis. So this particular joint is known as a spherical joint. So the common joints that are found are revolute joint, prismatic joint, cylindrical joint, and a spherical joint or a spherical pair. Now spherical pair is also found in our arm. So if you observe this, this is called as ball and socket, and also in our pelvis, that is also a ball and socket. That means I can't move it out, but I can have a lot of rotation that is possible. Okay, so that is about spherical. Now you may also try to understand from a different perspective. In a sense, let's say I keep a block. Okay, let's say I have kept a block on top of another plane. Okay, okay, let's look into 3D aspects now. This looks like a 3D diagram, or it may also be good if I just write a coordinate system stating that okay, this is a 3D problem and that is a 2D problem, like that. This is actually also, this is also a 3D problem, cylindrical. Okay, so now what are allowed, what is not allowed? It is very simple. So I can translate like this, I can translate in this direction so that it always remain on the plane, and I can rotate in this manner. So 3 motions are possible. What are not possible are I can't rotate here, this is not possible. I can't rotate here, that is also not possible. What else is not possible? I can't translate vertical, I can't lift it. Okay, so degree of freedom in this case is 6 minus 3. 6 was total allowed, 3 restriction, so that means 3 are allowed. Okay, so like that there are different examples that are given, so you may be able to go through them, and maybe I'll give you one more example. So imagine I have, this is now 2D. Imagine I have a curve like this, and there is a circular disc. Okay, so this is a very typical problem, so you should try to understand in different manner. Okay, if I have this body, and if I don't give you any condition of, let's say there is something known as slip or skid. Okay, I'll explain what they are. So let's say there is a circular disc and there is another curve surface. So how many, what is the degree of freedom? That is the question. Okay, now what you should understand is visualizing where all motion is possible is difficult here, right? However, visualizing where motion is not possible, that is easier. So what you can think of is, if I try to move this circular disc in this normal direction, okay, normal means normal where this contact is happening, so it will lose contact. Okay, so that means this translation is not allowed. Okay, however, I can translate in this direction, I can also rotate about that direction. Okay, so this translation is restricted, whereas the translation in the perpendicular direction and rotation is possible. Okay, so degree of freedom without constraint was 3 minus, if I reduce this constraint, in a sense restriction, so it will become 2. Now there's a catch here. So what is this 2? This is 2 if you assume slip or skid is allowed. Okay, I'll explain. So when you are going on a road, you on a cycle, if you hit brakes, what happens? The wheel stops, but still the wheel is moving, skidding in the front direction. Okay, so that means there are two independent motions. The rotation we stopped, but the translation is still happening, right? So that is similar condition here. Okay, the other scenario is, let's say you have a two-wheeler and you try to accelerate quickly. So the rear wheel or the power wheel will rotate faster and it will turn more, and then it will start moving. Okay, so that condition is known as slip. So there also you were rotating and the translation was happening. Okay, so that is when we have slip or skid allowed. However, if you assume an ideal situation where slip or skid is not allowed, that means there is a specific relationship between the translation of this and the angle rotated. So it basically, I have a disk, I start moving, so you can imagine that the motion, when it happens, it all these points have to be in contact, and when it completes one full rotation, that is 2 pi rotation, so the translation will be given by 2 pi into r, that is the circumference. Okay, so the translation is a function of rotation. So if that is the case, then obviously I can only assume that, okay, I'm rotating, hence translation is happening. So this guy will become the degree of freedom in that case. Okay, so there are different ways of looking at degrees of freedom of a pair. So as I said, first you should understand where motion is possible. That is one way of looking at it. Second, you can also see where motion is not possible, and accordingly you will be able to find out degree of freedom of a kinematic pair. Now very quickly I'll explain, in typical kinematics course we come across words called as lower pair and higher pair. Okay, what is a lower pair? Lower pair will have a surface contact. Okay, so example, prismatic joint, you remember there was a planar surface contact, plane surface were in contact. Then you also have revolute joint, some form of circle contact is happening. Circle is also a plane. Then we also have cylindrical joint, then we have spherical joint. So all these form lower pair because the definition is surface contact should happen. Okay, now there is also something known as higher pair. So in a higher pair there is a contact of, when surface is already ruled out, so what are the other kind of contact? You have something known as line contact, and there is also something known as point contact. Okay, for example, line contact is typically found in gears. Point contact, let's say we find it in cams. These are standard topics in kinematics. And if you go back here, the circle definition, what I have said, this is a point contact. There's a contact that is happening at point, so hence this will also become a higher pair. Okay, circle on line. So that is another example for a point contact scenario. Okay, so kinematic pairs we have briefly discussed, and in the next video we'll try to animate some of these kinematic pairs in GeoGebra. So for that, please stay tuned. Thank you.